Hello my dear students, this is Akash SD. Welcome to the ASD physics classes. Hope you all are doing really great. So students, in this video we are going to learn force acting on current carrying conductor, and we will also solve so many questions also. Okay, so let's start the video. So here you can see under the topic force on current carrying conductor, in a short form we can tell triple C, current carrying conductor. Okay, so say here, let an arbitrary shaped current carrying conductor is placed in a magnetic field B as shown in diagram. So here you can see one diagram I have taken. One magnetic field B is there inside the board, that means along negative z axis. After that I have taken here one current element, arbitrary shape. It's not like that, they will always give straight line here. Okay, and let's take current is flowing in this direction. You can see here by the pink color. So if I take very small length dl, then along the direction of current only I will take here one current element. What is given here? IDL. Okay, now what we are going to see here, magnetic force dF experienced by a small element of the current dl is given by. So I hope so you know this formula. The formula is what here? Force acting on moving charge particle F equal to QVB sin theta. Is it? Because current means a rate of flow of charge. Is it? So from here, if I just write here, very small force dF means you know very well current element is small, so charge will be also small only. So I can write here dq. Okay, and this charge will move with the drift velocity. We have learnt in a current electricity. After that, in the same way I can write here B into sin theta. Here theta is the angle between in this situation theta was the angle between velocity and magnetic field. But here in this situation theta is the angle between current element and the magnetic field. Okay, is it? Now after that, let's take here, this is equation 1. Now what we are going to do? We are just going to simplify this formula. So see here, if number of electrons per unit volume of the conductor is N, having cross-sectional area A, then small charge dq is given by. Okay, here also again I am writing here, see, this is called the quantization of charge here. Here I am writing here capital N because I just don't want to confuse with this small n and this small n here. Because normally we have learned Q equal to small n into E, but here n is what? A total number of electrons. Okay, so see here please, here I can write here, see, this dq is equal to how many total number of electrons? You know very well, n is the number of electrons per unit volume. So if I want to know total number of electrons, this number of electrons per unit volume, I have to multiply with the volume of the conductor, this very small length. So area of cross section is A, and the length how much here? DL. So volume will be A into DL. So this is the total number of electrons in a very small element, and we have to multiply with the charge of the electron E. Okay, so we have got here very small charge dq. Now what I am going to do here, from equation 2 I am going to put the value of dq in equation 1. Okay, so see here please, magnetic force dF experienced by a small element of the conductor can be calculated as. Okay, so see here please, here this dF is what is this? See, dq into Vd into B into sin theta. Okay, now what is the dq value? Can you see here? Na dl, correct, into E, and here we can write here, see, Vd into B into sin theta. Okay, now after that what can I write here? See, this dF is equal to, just let me collect all the things together, NEAVD. Now this N, this E, this A and this Vd I have collected together here. So NEAVD. After that what are the things is left here? Kindly see here, dl into B into sin theta. And you know what is this NEAVD? That is the current flow through the conductor. Okay, so from here I can write here what is the value of the dF. dF we can write here, kindly see here, the current is what? I. So I dl B into sin theta here. This is the force experienced by that small current carrying element dl. Okay, now if I want to write here in a vector form, in a vector form if I write here, remember that here in vector form it is given here, see here, dF equal to, we can write here I, and here I will write here this dl cross B. What is this? df equal to I dl cross b. Here dl cross b magnitude means dl into b into sine theta, but this is the vector form here. Okay. Now after that, let's see the next one here now. Hence, magnetic force F experienced by the arbitrarily shaped conductor is given by, because this is the force on a small current element dl. So if I want to know here the total force, what we have to do here? We have to integrate it. Integration of the df. Integration of the, what we have to do here? We have to do here the integration of the df. Each and every element will experience the force. We have to add all of them. So when I will write here, see, just I am writing here in a vector form here. Okay. So when I will write here the value of this one, so see here please, I am just writing here I, and here I will write here, see, this will become here integration of the dl cross b. Okay, see here please, integration of dl cross b. After that I can write here, hence F equal to, I am considering uniform magnetic field, okay, b. So only integration came here. Then after that, what can I write here? See, I, and it will become here vector L cross vector P. Okay. So students, this is the formula of water. This is the formula of force experienced by current carrying conductor in a magnetic field here. Okay. And see here, please, this integration of dl, where this one here, this integration of dl is the displacement length of the conductor. Very, very important, not a distance. Which length? Displacement length of the conductor. Okay. Even I can show also here. Let's take, this is the one end, this is the another end here. Okay. So just let me just show you here. This is the displacement length. From here to here, I am drawing here. This is water. This is the only displacement length. I can tell here this AB, A to B. Which length? Displacement length. Kindly see very well. Displacement length. Displacements you know very well. The shortest distance between initial and the final point here. Okay. Now after that, let's see the next topic here. Force on closed current carrying conductor. Okay. So let's see here. Net magnetic force on any closed current carrying conductor is 0 because its displacement length is a 0. What I am telling, displacement length is 0 here. If I write here the mathematically, kindly see here, this vector F, I can write here closed integration of df. Okay. So I can write here, kindly see here, I, and here it will become here closed integration dl cross b here. Is it? You are getting it? And you know very well here, whenever any closed conductor is there, its displacement how much? 0. That means this will become 0, or we can tell here, we will get here the null vector. And this is which force here? This is the net force, net resultant force here. Okay. So whether current is flowing in any direction, maybe current is flowing anti-clockwise, maybe current is flowing clockwise, any direction they are telling that here. Okay. In any direction current is flowing, does not matter. Net force I am telling. Net force how much here? 0. Okay. Remember that here. Now let's see, very important topic. The topic is what? See here. Equilibrium of current carrying wire in a magnetic field. Current carrying wire, current carrying conductor, anything, both are same only here. Now let's see here, see. In this situation, weight of current carrying wire is balanced by magnetic force here. Okay. So here what I am telling that here, let's take here, there is the one wire is there having its mass m. Okay. So anyhow the weight will act in which direction? Downward direction, mg. Is it? Now choice is there in which direction we should apply the current so that this weight should be balanced by the magnetic force. What is the formula? F equal to IL cross B. Even you can use the right hand thumb rule also, or you can use Fleming's left hand rule also. According to Fleming's left hand rule, if you will make this left hand, all the 3 fingers mutually perpendicular. 4 finger, what we call thumb, 4 finger, this central finger. So 4 finger will indicate the direction of the magnetic field. Central finger will indicate the direction of the current element, then force will indicate the direction of the force. Remember that here. Okay. So here what I will do here, I will just apply the current. I will make the current flow in this direction. Okay. I will make the current flow. Okay. Let me see. Current will flow in which direction? Let's see here. See, the current will flow in this direction actually, because right hand thumb rule. Na? Yeah. See here, this is the formula. F equal to, I am writing here, see, IL cross B. IL cross B here. Is it? I am going to use here. I will curl my finger from the current element to the magnetic field through the smaller angle. You can use Fleming's left hand rule also. So IL is this side, magnetic field inside, so IL cross B. So only the magnetic force should act in which direction? upward direction. Even you can check with the Fleming's left hand rule also is there. See, magnetic field is inside, current is this side, force is upward. So both these forces should be balanced here. So what I can write here, see, this Fm should be equal to mg. What is the magnetic force formula? Magnetic force, magnitude. Normally we know IL cross B, but if you want to know the magnitude, so here magnitude and here magnitude, then what this will become that here, see, ILB sine theta, is it? So you know very well, current element along x direction, magnetic field along negative z axis. So how much angle? 90 degree here. Okay, so I can write here, see, this one here, see, IL, let's take length is L, so ILB sine 90 means 1 is equal to mg. Then how much current will flow? Maximum to maximum time they will ask. We can write here, see, m by L into G by B here, is it? And what is m by L? That is called the mass per unit length or linear mass density. I can write here, see, lambda G by B. Remember that here, very very important, the current. Okay, so even let me write here in a bracket also, like this. Now, so remember that here, very very important, all these basics. After that, let's see here, students, what is given here. See, next topic, condition of maximum magnetic force here. So see here, what is given, see, when current element ideal is perpendicular, theta equal to 90 degree to the magnetic field, then, so see here, magnetic field now we have taken along x direction, and let's take the current element in this direction here. I can write here IL. Now let's take length is how much here? L. Some length is there. So I'm writing here IL, not ideal. No, because some length is there. So how much angle is there? You can see very well, magnetic field x direction, current element y direction. So maximum magnetic force will be how much here? See here please. ILB sine theta. So ILB sine 90 degree, is it? And this will become here what? Kindly see here, ILB. Very very important. Okay. Next one, let's see. Condition of zero magnetic force, very important. So now let's see what is given here. See, when current element ideal is either parallel or anti-parallel to the magnetic field, then only it will be zero. So see here please, magnetic field along x-axis. First I have taken here current element, let's take in this direction IL. And here how much here? Same direction, that means here in this situation theta 0 degree. But if I take reverse direction, let's take here ideal, then in this situation theta how much here? 180 degree is there now. And what is the force formula? Force formula you know very well here, as magnetic force F equal to ILB sine theta. And you know very well here, either sine 0, sine 180, both are 0 only. So how much will become here? It will come here 0. Okay. So remember both the situations. Is it great? Now we are going to solve some questions here. Now, so see here. First question, a conducting loop carrying a current I is placed in a uniform magnetic field pointing into the plane of the paper as shown. The loop will have a tendency to. So again I have told you which kind of loop is here. This is the closed loop is there. Closed loop means here how much net force it will experience? Zero net force. So zero net force means anyhow it will not do any translational motion. In the absence of net force, the loop cannot do any translational motion. That means option A is also not possible, option C also not possible. So either loop will contract or expand. Okay. So here we have to identify in which direction. So you can see very well if I talk about here at this point here. So at this point you can see here, very small current element, ideal is this side and magnetic field is where? The magnetic field is inside. So curl your fingers from ideal cross B, current element to the magnetic field. Now, so what is happening that here? The magnetic force will coming in this direction. All will be mutually perpendicular. Okay. So magnetic force in this direction. Let's take very small force, DFM. So what will happen that here force in this direction, DFM here. Okay. So this is the force. Similarly, when here you will see force in this direction, force upward, downward, now like this here. See, like this forces will act here. Like this forces will act here, is it? So you can see very well here, individually the forces are acting. But if you see the resultant force here, what will happen? The resultant force on this wire is how much here? 0, because this is balanced by this one, 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 is it? So all of this small df is there here. So all are forces acting in outward direction. That means what will happen? This one will expand, option D. it will expand option D. If in case they reverse the current direction, instead of clockwise they made it anti-clockwise, then it will contract. Why? Because all the forces will act inward here. Okay, remember that here, very very important. Now very basic question. Now let's see, the question is what here. See, the question is, a circular coil ABCD carrying current I is placed in a uniform magnetic field. If the magnetic force on the segment AB is F, the force on the remaining segment BCDA is how much here? Okay, so here also again you can see the situation. So before also you have seen that here, no? See here, the net force was 0, no? Current was clockwise direction. Here also current is clockwise direction here. But now we'll see from the different point of view. So see here please, the net force how much is coming here? 0. Net force 0. So what I can do here, this segment, no, they are telling the force on the segment AB how much here? F. So I can make here segment AB, no, because net force is there in a vector form. So FAB. After that, next segment overall to complete the loop, BCDA. See the students, BCDA. Now this will come how much here? 0 here. Is it? That means if I calculate here, the BCDA will experience how much force here? See, BCDA, no? That's send this side here, so minus of FAB. And FAB, how much they are telling that here? F. So it will become here minus vector F here. Okay. So very simple. If AB segment is experiencing force vector F, then BCDA segment will experience force minus vector F. So that net force on the loop should be how much? 0. Okay. So what is the correct answer? The correct answer is here, option A is the answer. F minus F means direction is opposite but magnitude is same. Okay, great. Now let's see this question. A triangular shaped wire carrying 10 ampere current is placed in a uniform magnetic field of 0.5 Tesla as shown in a figure. The magnetic force on segment CD how much here? They are asking magnetic force on the segment CD how much here. Okay, so this is the segment CD, and you know very well here, if I will connect this with the dotted line here, so 5 centimeter, 5 centimeter, this will be also 5 centimeter. Is it? That means this angle will be how much here? This angle will be 60 degree here. I am just focusing on the segment CD. Okay, now magnetic field in this direction. Let's take here, see the magnetic field in this direction. This is the direction of the magnetic field. Now the current element, now let's take see the current element along the direction of the current and magnetic field will make how much angle here? Think and tell. This angle will be also 60 degree because alternate angle. Okay, so if I calculate here the force on segment CD as of now according to the situation, then what is the formula here? ILB sin theta. Okay, ILB sin theta. Now what is the current? Current how much is given here? You can see very well. The current is given here 10 ampere. So 10. Okay. After that, length how much is given here? See the 5 centimeter. That means I can write here, convert into the meter, everything in SI, no? Because see the options. Newton is there. 5 by 100. Magnetic field B is how much given here? 0.5 Tesla. So 0.5 Tesla means I can write here 5 by 10. Sin 60 degree value, no? Because sin 60, sin theta, sin 60. So what this will become here? Root 3 by 2. Okay. So let's cancel out the things. You can see very well this 0 is cancelled, and this we can write 5 2 is 10 and again 5 2 is 10. So this will become here root 3, 2 to 4 into 8, root 3 by 8. So root 3 by 8, when you will simplify this will come here 0.2165 Newton, maximum to maximum. Okay. Just it will come 0.2165 Newton. So which option is correct is there? Option C is the correct answer. Even if in case, now see here this one we have got 0.2165. But if in case they are asking here what is the force on a complete AE wire, then you know what will happen that here. This is starting from here and ending here. This will be the displacement length. Now, so this complete wire, this wire will be replaced by one straight wire. Then all current element this side, magnetic field this side. Then on the AE wire, how much force will be there? 0. Why? Because full AE wire will be represented by this way and magnetic field is this way. So they are making how much angle? The current because this side here. So they are making how much angle? 0 degree. So force on the wire AE will be how much here? 0. CD they ask 0.2165 Newton. Even on BC also we can calculate, not a problem, but net force on AE will be 0, but here in this question 0.2165 Newton here. Okay, remember that here. Next one, let's see again. One basic question is there. See, this is the diagram is there. See, a single turn current loop in the shape of a right angle triangle with sides 5 centimeter, 12 centimeter and 30 centimeter is carrying a current of 2 ampere. The loop is in a uniform magnetic field of magnitude 0.75 Tesla, whose direction is parallel to the current in the 13 centimeter side of the loop. See, 13 centimeter and current element, magnetic field direction same. Now see, the magnitude of magnetic force on the 5 centimeter side will be x by 130 Newton. Then the value of x is how much here? Okay. So again you can see very well, closed loop is there. No? Closed loop is there. So the net force will be how much here? The net force will be 0. Correct? The net force will be 0. After that, let's see here please. I can write here. Some segments are there. No? 5, 12, 13. So let's take here 5. F5 plus F12 plus F13 is equal to how much here? 0 here. Is it? I'm just telling you. Then what will happen that here you know very well, on F13 how much force will be there? 0 force will be there. On F13 how much force is there? 0. Because magnetic field upward, current element downward, 0. Okay. So what will happen that here? This term, this F13 will become 0. Okay. 0. Hence what can I tell here? The force on 5 centimeter segment will be minus of force of a 12 centimeter segment. Okay, I am just telling you. So force on 5 centimeter and 12 centimeter both will in a which direction? Opposite direction. Remember that here. Okay. After that, if very easily we can calculate force on the 5 centimeter segment. Formula kindly see here. ILB sin theta. Directly also I can do here please. Now see, directly I am doing now. So now see here please. This 5 centimeter segment, how much current is flowing here? See, it is given here the 2 ampere. 2 into length of 5 centimeter segment is how much is given here? Anyhow 5 by 100. Okay. And B, magnetic field is how much is given? 0.75 Tesla. So I can write here, see, 3 by 4 into sin theta values. Theta, this is the theta. So in this triangle you know very well, sin theta means opposite by hypotenuse. So opposite means 12 and hypotenuse how much here? 13. So I can write here 12 by 13. I am just calculating the pure force. Okay. So what is happening that here? Just let's simplify this here. So here when you are simplify this, what it will happen that here? See, this 5 and 5 2 ja 10, 20, and this will become here 2 10 ja 20. Okay. So we can write here, see, 3 into 12 by, we can see 10 into 4 into 13. Okay, but we should get here how much here? We should get here 130. Okay, so this 4 is there now. See, this 4 3 ja 12. So 3 into 3 9 by 130. How much is getting here? See, let me write here again. I'm writing here. It will come here 9 by 130. Okay, so what is given here? X by 130, and here what is coming? 9 by 130. That means what is the value of the X? Value of X is 9. Directly I can get. But why I have done all these things? Because see here, if I talk about this one here, see. Now, so very simple what I am telling you. Whatever force is acting on 5 centimeter segment, opposite direction force will act on 12 centimeter segment. Okay, and the magnitude will be same. So 5 centimeter segment is experiencing how much force? So this one 9 by 130 Newton. Okay, similarly 12 centimeter segment will also experience how much force? 9 by 130 Newton, but the direction opposite. And this segment will experience how much force? 0. So net force on the total loop will be how much here? 0. Okay, great. Full basics I am telling you. Now students, let's see this question, the very easy question. See, question is looking big, but very basic is involved here. See, a massless square loop wire of resistance 10 ohms supporting a mass 1 gram hangs vertically with one of its sides in a uniform magnetic field of 10 to the power 3 Gauss directed outwards in the shaded region. A DC voltage V is applied to the loop. For what value of V, the magnetic force will exactly balance the weight of the supporting mass of 1 gram is there. Now, so based upon the balancing situation, question is there here. So see here please, magnetic field in which direction? Outward direction. Is it? So let's say here, current will flow like this. Okay, positive to negative terminal. Now you think very well. See here please, weight is hanging downward. So you can see very well the weight is downward, mg. Is it? Weight is downward, mg. Now magnetic force will act in which direction? To balance it, upward direction. Even you can check also IL cross B. IL left side, magnetic field is outside, so see IL cross B, IL this side, magnetic field also, IL to B, I will turn the finger, so this one here, the magnetic force on this wire is upward here, is it? So what I can tell here, see here, I am just writing here, see, this will become here, see, this magnetic force Fm is equal to mg, okay. Now after that, let's see here please, Fm, how much it will become here, kindly see here, ILB, sin 90. Why sin 90? Because current element along negative x direction, magnetic field along z direction here. No? So 90 degree, ILB sin 90 degree is equal to how much is coming here, mg. And after that, what can I write here please? They are asking the voltage. Now we'll apply here the Ohm's law. So I equal to what is given here, see, V by R. See from here, V by R LB, V by R LB is equal to mg. So from here, what is the value of the V? Kindly check out please. It will become here mgr by LB here. Now, then after that we have to just put the values now here. Now let me put here the values. So M, mass how much is given here? You can see very well. The mass is given here the 1 gram. 1 gram means convert into SI, 1 by 1000 kilogram. 1 by 1000. After that, the gravity how much is given? Gravity, it is given here the 10, okay, into R value. Resistance how much is given here? Kindly see here, the resistance is given here the 10. Resistance is also 10. Length, see here, see. Sides of the loop is 10 centimeter. Now that is the loop, side of the loop, this loop, 10 centimeter is given here, okay. So 10 centimeter is what is coming here? 10 by 100 into magnetic field B. Magnetic field is B. How much is given here? Kindly see here, 10 to the power 3 Gauss. So 10 to the power 3, 1 Gauss, how many Tesla? 10 to the power minus 4 Tesla. 10 to the power minus 4 Tesla. Okay. So after that, you have to just simplify this. This 2 zeros, this 2 zeros cancel. So it will become here what here? 1 by 10. Okay. Here what will happen that here you can see very well, 10 to the power 3 into 10 power minus 4, that means 10 power minus 1, 10 power minus 1 and 10 will balance. So it will become here 1 by 100. So 1 by 10 by 1 by 100 will come how much here? It will become here, I can write here the value of V is going to be how much here? 10 volt here, 10 volt. Okay, so the value of V is coming how much here? 10 volt is there, 10 volt. Okay, so anyhow the 10 volt, the value is there. Can you see very well? NET kind of question is there here, not NET, MCQ is there, see, this option D is there, 10 volt. So students, I hope so, this video based upon the force acting on current carrying conductor and we have solved questions also is very clear to you. Keep studying, keep growing.